Today, we're going to explore machine learning and deep learning framework that has been open sourced by Apple for the first time ever. Like, have you ever heard anything being open sourced by Apple? Wow, that's amazing. So, I'm excited to see this. I have not read it at all. I just opened it. I just got to know that Apple has open sourced a framework, ML framework, basically. For the like, I have not, I've literally not heard Apple open source. Maybe a gap in my knowledge, but it's just I don't know. Okay, so basically the whole idea is let's read this through. So I mean, MLS is a NumPy-like framework that is designed for efficient and flexible machine learning on Apple Silicon. So basically, I also have an M1 Mac, which is the silicon chips introduced by Apple recently. So that has been brought to us by Apple Machine Learning Research, and the Python API closely follows NumPy with a few exceptions. MLX is also a fully featured C++ API, which closely follows the Python API. So the basic stuff, you know, and it also has all of these uh, it is also like it is written here. The design of MLX is inspired by frameworks like PyTorch, JAX, and NR framework. A notable difference from these frameworks and is unified memory model live in shared memory can be performed on any of the supported devices. Okay, so this is basically it, and I don't have a GPU. So yeah, so let's get started by first installing this thing, right? MLX. Okay, so let's see. I'll open my Visual Studio Code. Get started. MLX. Right. Hold it all. Not working. PyCharm. Patterns by N from error. PyCharm uses the VENV by N, and somehow uh, it is not getting pip installed in the pym environment. Let's see if it is here. Well, pip flex. Okay, so we have a working version 0.1. Okay, cool. So let's see. Let's start with a new file. And okay, so what we're trying to do, what can we do to compare MLX with the other frameworks that are available to us, PyTorch? Basically, in this video, what we can try to do is we will try to solve a very basic problem. We'll go back to the basics and go with the MNIST data set. Very simple. Use the examples available here. Create a simple convolutional neural network model if that's possible. We'll see. We'll explore all of the functionalities that are available to us in MLX, and then we'll make a same model in PyTorch with similar hyperparameters and similar configuration, and we'll compare the training time difference between both of those models when we are trying to train and keep everything else same, right? So that's our objective for this video. So I think that will give us good enough results in terms of performance comparisons when we talk about MLX and PyTorch, and more specifically on an Apple Silicon, because right, they are saying here that it is efficient and flexible machine learning on Apple Silicon. So I think they must have done some optimization based on the particular hardware that they have used inside the silicon chip. So there should be some performance improvements logically, but let's see if it is actually there. Right. So let's see. Let's start with it. So I've already pip installed it. Uh, Pip install MLX. That's the basic stuff. That's the only thing I have done till now. Okay, no typos, please. So requirement already set it right. Yeah, I don't know why. Okay, cool. So I've done that, and let's get started with the examples, right? Multi-layer perceptron examples. So I think there should be an example with the, I think I saw an example with the MNSG dataset here. So here it is. Let's try to understand this, change the model parameters a little bit. They have used the linear layers in this example, I think. Uh, uh, right, there it is, right? Self dot layer, so the nn dot layer item. Um, right, so this is basically list comprehension if you're aware of it. So yeah, so the you can see the framework is kind of very similar to PyTorch. We can observe that in the first instance they have used the same nn dot module for class definition of a model, and then what we are doing is we are defining a loss function, uh, which they are also taking in. It is not really necessary to do this, but I think they have done that to make it easy. So then we have a eval function. Eval function, yeah, I guess it evaluates the y, like the y with the maximum probability from argmax, right? So there's that. I think it's accuracy, right? Yeah, you're trying to compare for how many instances this was correct. The output was the desired output. So I think this is some measure of accuracy here. For yeah, they say it right there. Okay, so I don't need to use my brain so much. Everything is written. We just need to read here, right? So okay, great. So next we set up some parameters. Then we import them. Okay, let's get started with it. Not too much advantage in reading everything. Let's just import mlx.core. I don't know why is it. Why is PyTorch not able to find this? Code could not be resolved. Violence missing imports. Weird, right? So if I use Python, I say mlx dot underscore version. Does that work? Yeah, import mlx. Does that work? Okay, it is working. So I guess it should work, right? Let's see. Import numpy as num. I don't know why don't we need to import numpy anymore. If we are, if mlx is a framework similar to numpy, as they have mentioned it, I think it's more similar to PyTorch, no? Considering the functionalities we are getting here. Like there are API calls to Python, array as type. This is, I think, this is all of the part where they mention it being similar to NumPy. Devices and streams. Wait, they must also have a metal device, right? Right. I mean the metal processor that uh, Mac has. What devices do we have? Okay, that's fair, I guess. Default device. Stream. Let's ignore this. Operations. Okay, cool. That's very easy to use, I think. Considering all of the names, they have kept it very similar to the other libraries that are available to us. So that's great. That's nice. Otherwise, it would have been a lot of headache. I've been also been working with Rust lately. Like, I wanted to start a series where we can make some ML models from Rust from scratch. Uh, that would have been pretty cool in terms of understanding machine learning algorithms themselves and also having a go through Rust. But when I came across the Rust libraries, they are not so straightforward. Like Rust, it's in itself has a very steep learning curve. But when it comes with its libraries that claim that they are inspired from the other libraries that are available for Python, they are still clearly very different. So, but we'll do that. We'll make a series on Rust, no matter when. We'll definitely do that. So we have layers here, convolutional 2D, dropout. So the layer names, they have also kept very same. Um, right. And they have also introduced a transformer layer directly. As far as I see in PyTorch, whenever I had to use transformers, I had to basically define my own transformer layer. So that's convenient. I don't know if the current update of PyTorch does include transformers in it. So okay, that's cool. These are the optimizers. Okay. Let's not get too much into the theoretical part of things and let's just get started. So let's define our class MLP and dot def in what do we need? I think we need all of this. We just need input dimensions, output dimension, and so super dot net for layers. Let's define what they're right. So okay, so what we can do is just self dot layers equal to, I think this should work, and then dot let's start with a convolution layer, right? And let's see how their con2d layer works. It's a good practice to just read the documentation and work your code from there. Gives you a good chance at understanding the core functionalities and also makes you a better coder in it. So let's see. So input channel, output channel, the basic stuff, and the kernel size, right? The padding. Okay. So it's very similar to PyTorch, which is great, amazing. So the input channels will be three basically. It's MNIST, right? The input channels will be one and four. Okay, let's see. The input channels will be one for EM, and let's do 32 first layer, and let's keep the kernel size to be 3 and padding to be keep the size same. So initially when we have an input, okay, we'll do it during the forward layers. So yeah, so basically we have an input of so how what you all must be aware of the sizes that the MNIST dataset has. So in the input we have a 28x 28x image of one channel because it's grayscale. Then we what we are doing is we are passing through it a convolutional layer. So the one channel will become 32 and the image size it's 28 by 28 image size. So if I keep the padding 1, the size will remain same because the kernel size is 3. So there will be one padding here and one padding here, which will uh, not decrease the size of the image. But if I have to really do that, I think I use, yeah, let's padding and then you use the pooling layer, right? So channels and we'll have padding. So 28, so the our, output of our after our second layer would be 28x 28 into 32, right? And this is after first convolution, and after that we can use nn dot, let's see how are your pooling layers defined. Okay, I don't find any. Do I not have any functions? Okay, work around that. have any post network and get the speed of it. I just wanted to make a deep network so that we can get a good comparison between. So it's fine. I think is I will just use padding here. So now the size will be 20. Then use another cone. For that, we should use. How did they define it? Find it in a weird manner. They use. They did not use any non-linearity in this, right? They didn't. Yeah, well. So why they are not using any non-linearity? Is this mx dot maximum? Element wise maximum. Mx dot maximum. That takes the element wise max of two arrays. Compile style broadcast semantics. Input arrays. The max of a and you mean by element wise max? Okay, it outputs an array. Okay, I get. Okay, okay. So you're using an max between. Oh, okay, okay. So you are defining ReLU basically, right? Okay, that's cool. So yeah, we can do that too. Just use ReLU activation. That's cool. So yeah, we'll do it like them only. And let's just this. Now we have 32 channels to 64 channels. The kernel size remains the same. Now after this, we'll have after second convolution. This is the output after first con. This is the output after second. Would be 4 into 24 into 4. Okay, that makes sense. Now let's see what we can do with this. So I directly use this, but really wish I could find an implementation for pooling layer. Otherwise, we will have to self-implement it, which is not that difficult. To apply a pooling layer, must be a function, right? A convolution function. Convolute, maybe something. But yeah, solve con 2D. So put weight channels, input channels, and output H W. Python version that doesn't mean by wait. Okay, wait. Try this. So let's have another file for. Let's save this as st. So then experiments. That's important. Let's define a list basically. So uh, one is okay. Let's see. How can we take a good example of this? So the example I'm trying to take here is, for example, so I have a 4 by 4 array basically, right? And if I apply a 3 by 3 convolution and let's apply average pooling. So to apply average pooling, what you have to do is just keep, you have to scalar multiply these two matrices, right? Yeah, you have to basically multiply these matrices, and in the end, you should get a single value, uh, right? So, and the values of these matrices we keep as 1 by 9 of them. That's how we do average pool. And we do these form of convolutions of once here, and then we do one here, then we do one here. And so if we apply a 3 by 3 convolution on a 4 by 4 matrix, the output would be 2 by 2, which makes sense, right? So this much is understood, right? This is how convolutions work. So if I have to apply so let's make an random array. So let's say we have an array of all ones in here, right? You get the idea. So one, wait, so that gives us a, we have to make a for matrix. This is how it's done. So let's print the array, and you will get. So we have a 1 by 4 by 4 matrix. So now what we can do is let's so how do we convert this into an MLX array like we do for NumPy arrays? Let's see. So array dot array is tuple and okay. X dot. So this should work, and let's print error. Oh wow, did I just again? And so yeah, now we have an MLX array of int 32. Now we have to define another array that will be our convolution, and let's define it as MLX dot array. And now we want 3 by 3 convolutional layer of weights 1 by 9. So 1 by 9 into 3, 4 underscore in range 3. I hope these list comprehensions make sense to you. So now that I've done that, and now if I print my array 1 and array 2, that they have the values that we put in. Right now, if I apply convolution, um, then so what I'm trying to do is we'll use the array functionality in mlx.core. Open. Here we have a function known as cont2d. So mlx.cont2d weight arr1 and the weights being arr2. This should give us arr3. What should arr3 be? Now the question arises. Basically, according to my understanding, when we apply this on these weights, right? So we multiply them element wise and then we take sum of it, right? So what happens is, so what will happen is 1 by 9, 1 by 9, 1 by 9, 1 by 9 for all of these weights, and then it will be sum. So it will give us 1 again. There would be some floating point imprecision, so that's not really something we need to worry about. So this should give us 1 1 1 1, basically a 2 by 2 matrix that has 1 1 1 values. So let's print arr3. Let's see if this works the way we want. Oh, okay, now we are getting an error. Invalid input with type array. Convolution currently only supports floating point types. Great. So what we have to do is we can define type here, right? D type, right? Great. So D type will be, then an examples for D type. I guess I can just write 32. Let's see if that works. Let's just another error. Invalid input with 2 dimension for 2D convolution. Created an array with 4 dimensions. Following the format and see. Okay, okay, okay. So okay, it's fine. So I hope there is a dot. If it's inspired from PyTorch, there must be what view function. Go to the array operation. View. There was reshape and view in it, right? So let's just say view, and we want the view to be 1, comma or 1. MLX has a view and does not have reshape. Okay, so we do have a reshape, and it did work. Great. So we can use same for this. Not sure. Look, I think size. Okay, so we did get it. We did get what we want. So here are three. You observe this. This is the metric that we expected to see. Like, let's see the shape of it. It is right. So we get a 2 cross 2 matrix uh, with one channel. Okay, so this is what we can do to obtain convolution, right? Like average pooling in here. So let's apply these. Let's apply it as a function, right? So yeah, okay, okay. So basically, we'll apply an average pool here of size 2 by 2. And one more thing about uh, average pooling is that we have a stride equal to the kernel size, right? So there must be a stride in here too. Let's see that. Like if for instance we were using a 2 by 2 matrix here, so we'll have to use 1 by 4 first of all. And other than that, if we were using average pooling, proper average pooling with a stride, then the output size should remain the same even after we have reduced this, because basically we will not be repeating. Like here what we're doing is uh, we went through these, then we went through these, right? So this these two columns were repeated in both of the convolutions. But when we talk about uh, if we put a stride, what will happen is if we have a 2 by 2 matrix and we have a stride, so basically if we have done this, we'll not repeat any of the columns, we'll have a stride basically means the number of columns you want to skip, right? So if you have a stride of 1, so was just skipping one column, so it was just going here, right? So but if you have a stride of 2, it will start directly going here, and so there will be no repeats. So basically this will give 1, this will give 1, and again there will be no repeats. So this will give 1 and this will give 1. So let's see. So does the conv here on 2D, where did it go? On 2D must have a stride is good. By default it must be 1, default 1, right? As I was saying, so if I repeat the same, it would give me a 2 by 2 matrix again by the same logic. And if I print that matrix, it should be 1 because I'm doing average polling and all of the values are 1, so it will remain 1. I don't know why I write such a. Yeah, so there you go. We get 1 1 1 as we expected. So this works the way we want it to. So we can use it during the forward pass. Now let's think about. Okay, so we have these two. So we'll apply a convolution here. So this will become 13 by 13. So let's keep adding now, right? Just to keep. So this will give us 14 by 14 now. And then if, these 14 will 14 pass here. Then we are applying one without stride, so it will convert into 12 by 12. And then that 12 by 12, after that we'll be applying a pooling layer again. It will give us 6 by 6. Right, and I think this should be enough, and then we'll directly use a linear layer which will take the size of 6 cross 6 cross 64, which is uh, 36. 6 into, that gives us to 4, convert it to 10. Right. So now we have defined our layer, right? Great. Now the model has been defined. Now what we can do is let's define the forward pass. So this is how they have defined their forward passes in, I think, also X example. So yeah, so they have self and box X layers with the last one and dot. Dot. Basically, what this function is doing here, just applying relu activation. And here, um, do you use pooling layers before activation or after activation? So solution order. Like convolution theory from these links, that order of convolution is here. I've tried to explore a convolution operation X, but there is no activity met. Might as well time and first, thereby reduce. So ideally, you should do pooling first, right? So let's apply a pooling layer here. And how are we gonna apply the pooling layer? To apply pooling, we'll do mx dot con. Now this is different from the above conv2d. It was a neural network conv2d, and now we are using a basic function of conv2d, and we are going to do that with a matrix that we defined earlier. So mlx, this will apply our average pooling for a 2 by with a 2 by 2 matrix. So it is what we're trying to do is basically reduce the size by half. So we'll use this, and also, right, so this is our weight, and also we'll have to use the stride of 2. So this should be this, so this mx dot maximum is our activation, this mx dot conv 2d with the our output from the layer, and then uh, using a convolution filter of size 2 by 2 with 1 by 4 to average pool, right, with a stride of 2. And right, so this is the this 0.0 is the part of mx dot maximum, which is basically the relu activation. So this is done, and for the last layer what we'll have to do is return, and also we also need another activation function here. I hope we have that defined, otherwise we'll have to define it, which is no big deal again. But let's see. We do it did add an activation relu. I don't know why we didn't use it, but it's okay, it's cool. Have it, should we not have sigmoid activation or softmax for that instance? Softmax. Yeah, we'll have to also apply soft. There are some gaps right now in the MLX library. You can work with that. So let's implement a softmax. How to implement softmax? Softmax to average the values in a way, it is a weighted average of values, so that so for example, when we are talking about this, so we have a 10 class classification, right? So in a 10 class classification problem, we'll have an output of 10 classes, and each of those values in that array, corresponding to that index, would represents the probability of that value being our true value. But when you are comparing these values directly, they can range from any number to any number, as you are not defining any kind of control over it. So when we use a softmax activation, what we are trying to do is we are trying to have a weighted average of them in a way, not even weighted average, if you know normalization, right? So we are basically trying to normalize these in a weighted way, so that the one that has the maximum value gets the maximum weight, which is the maximum value. And when we sum up all of these values, they should sum up to one, so that they represent probabilities in the most theoretically correct form, which helps the model to learn better, right? That is the idea. So let's see. So the formula for softmax, the exact formula you can find here. So there you go. It is just, and do you know why we use exponential in the softmax function? So basically, the exponential is used to prevent us from like mathematical foundations. So example, for instance, if all of these values sum up to zero, or relate extremely close to zero, then this value would increase to a very high level, right? And this would cause us precision issues in terms of like the computational power and all of that. So we use exponential, so that these values, even if they sum up to zero, right, we will using the sum of their exponents, and that can not be zero anyway, because all of these values can never be zero, and the exponential will prevent us from such, basically. So that's the idea. So it's preventing us from some mathematical instability that can happen. Now let's see. um okay, so let's apply softmax here. We'll receive a mlx.array of size 10, and what we want to do is, first of all, we want to sum their exponents. So for, so sum is equal to 0. So basically, denom is equal to, for I in x, denom plus equal to e. How do we define e? It is math 30. Okay. E into, that will make up our total, and we output array equal to math put into I divided by denom for I in x. Convert it back to mlx.array. That's our softmax. Right. Not work for a batch size greater than one. Have to treat it like one comma like this. We'll have to do it like this. So I in x right here for x are the total number of batches, right? So in batch in x, I in batch, denom plus equal to yes gives us that. Then we'll append out dot append all of this, right? And have out dot append all of this, and also don't even need to do right now. Out dot append this, also return x dot array out type dot float. Let's quickly verify this. So for instance, we have a array that has values 1, 0, and we have another array. The size is 0, 1, 0. Another array has 1, 1, 0. Let's make it 1, 1, 1. The difference. Right, and all of these arrays are stored inside one array as a batch, as a two-dimensional array, which is right. And this is an MLX dot array with d type is equal to MLX dot. Let's print out our array. Great. So this is we made our array. Now let's apply a softmax on it, our defined softmax. So let's print softmax if it works. The math is operand type text array print I. What is I? So I dot value. Do we take out the value of how else can any indices? How do we take out the value then? Let's wait. So dot item. Okay. I dot item. There. So we'll have item. Put it operand type. Okay, great. So this next to core array. Till there. Out dot append. Here. Oh yeah, it's dot item. Item can only be called an array of size 1. Prime batch. Uh, print state. Great. So we now have a working implementation of our softmax. So as I was telling you, so I just wanted to keep these values so that it is more clear to you. So as you can see in the first value, the first is the maximum weight, and all of these are smaller values whose weight should be equal, right? If you're talking in terms of probability. So therefore, these three have the equal weight, and this has the maximum weight. Now in this one, these two have equal weight, and these two have equal weight, and in this one, these three have equal weights, which is higher than this one. So that's how softmax works, and we have basic implementation of softmax that works for any batch size. So that's great. So this is working now. Let's go back here, and now that we have a working softmax also working, now we can just do return softmax of our self dot layer. That's what we want in the end of it. Yep. So now we have a model defined that took longer than expected. Now we just have to copy everything else. I'm just writing everything by hand because it's a good practice when you're reading a documentation or something. Don't just copy directly code. I know you understand it while reading it directly, but you just sometimes get a hang of it. and also get some practice done. And also, other than that, you are also able to see the minute details while you're typing it word by word, and maybe you will observe something new or something interesting about the way we write code in here. So basically, it's pretty basic. There's nothing much into this one, but this can help in some instance. So now let's just try val function for model and x y mean x model dot mean mx dot rmx model 1 to y. Okay. Now let's see this. Don't need just need input. Let's for import mni module. Set data you need. Okay, so they themselves. So let's use their code right now. I don't want to dig too deep in the data processing part of things that for the day. Right now, I just want to compare the I. Now what I do is in image in label test images labels map. So this loads our data. This is their code to great. So now we have loaded the data, we have implemented softmax activation, we have also implemented our convolutional average pooling using a convolution filter, because there was no direct implementation of average pooling in this module, and there was no direct implementation of softmax 2. And now we have defined a multi-layer perceptron network. Let's not call it a multi-layer perceptron because it is basically used for fully connected networks. Let's instead call it a CNN, and just for the sake, because we are keeping it a bit different from them, we are not trying to use feed forward layers, we are trying to explore convolutional neural net. That's all. That's great. So it is very similar till now to PyTorch. I can't see much of a difference, which is great, which is very easy to use, and it's working very smoothly. Honestly, like in the experiments too, you can see I'm making arrays. All of this. This is very similar to NumPy. This is how you do it. This is also very similar to how you do it in tensors also. So that is all great. This is all amazing. Now let's go ahead and let's start with the training loop, as we have loaded the data now to the MNIST data set. So let's first of all we have to make a loop to create batches. So we'll input the batch size here. I'll not try to do too much experimentation on these parts because this is pretty standard. We can change it later on, the batch sizes and stuff. So I will not worry too much about it. I'll directly copy their code, which is written here, and then we can start focusing on performing the experiment, and then comparing, then making a same model in PyTorch to compare it with the performance, right? So I hope this all is making sense to you till now. Perhaps. Um, So we need iterator here. You're aware of Python iterators using yield, where we can use dot next. So, and we have used the SGD optimizer. Do we have an Atom optimizer? Like, here is a unsaved bias towards Atom optimizer. Just amazing. Anywhere you will read about it, you will just read good things. So, I don't want to use the SGD optimizer. I just want to use the Atom. That's what I've been using, and I love it. So, Atom, basic Atom. It works. It just works out of nowhere. So basically, optimizers, Optim. So okay, great. So we have Atom. So in here, instead of using the SGD optimizer as them, where it is. So let's call our model. A model is equal to CNN. Now we have to give the input dimensions and output dimensions. So I didn't really use the output dimensions, but here it should have been output dim instead of 10. Just make, and the input dim, I think I did make use of it. No, I didn't. So I basically didn't use it. Do we need to use it though? Where did we use the input dim? So here they use the input dim, but we are using a convolutional layer, and the convolutional layer doesn't need the dimensions of the initial input. So we can skip that. Right. So we don't even need this use. We don't even need input dimensions because we have constructed the network in such a way that can only work with a 28x28 image, which is the size of our MNIST dataset. So, okay, I hope that all is well understood. Now, let me just quickly check if we have not made any mistakes using neural networks and conv2D layer. There it is. Now, input channel, output channel, kernel size, stride, bias, and we don't need anything else. Do we have an input layer in itself? Because that is what we have to do sometimes in our PyTorch, right? You have to define the input layer by yourself. So I think we don't, because it's not mentioned here, and it should have been if it was necessary. If they have not, school. So this all should work. Now the batch, we have used the batch iterator loop, and now we have to define our model. Let's ignore the input dim. We don't need that. We just need the output dim, which is the number of classes. Fine, let's calling it output dim. So it's 10, and then mx dot eval dot parameters. Okay, so that's not something we do generally in PyTorch. I don't know what the eval is doing with the model parameters. And we are also defining a loss and grad function. Okay. Okay, so this is where it starts to get different. This is not the this is not so similar to PyTorch as similar to we were PyTorch here. Okay, so let's see what all this is. Optimizer is equal to optim.atom, our favorite, and we'll pass on just the learning rate here. Okay. In PyTorch, we also pass in the parameters. We pass in the parameters here. So I guess instead we just pass into mx.eval or mlx instead of passing it to optimize. I don't know what differences it brings to the table, but that's fair. So let's keep the learning rate to what they have kept it to. What's your learning rate? 1e minus 1, so 10 to the power minus 1. Yeah, that's fair. Let's keep it. Why not? E is not exactly 10 to the power, no, but it's in the same order. So basically, it's E is somewhere around 2. So e to the power minus 1 somewhere around 1 by 2, which is 0.5, but it is of the same order. So we just consider them to be the same value, right? Because in terms of learning rate, when you are talking about machine learning models, 100 and The learning rate of 100 and the learning rate of 500 doesn't make much of a difference because they are of the same order, right? They have the same number of digits, they are of the same hundredth order. But it starts to make a difference when you are rising up on the 10th order. Now, this is not a set rule, but it is a general observation, right? So, okay, let's keep the learning rate to be 0.1. Or maybe we can decrease the learning rate because we want to train it for more iterations because we want to compare the speed. So yeah, let's keep it lower for now. And for e in range num epochs, what are the number of epochs they are using? We'll use 10 times. So oh, they are just using 10 epochs. And for x comma y in batch, it batch train in train plus function model comma. Okay, let's see. So their loss and grad function they have defined using the nn dot value and grad. And in nn dot value and grad, they've used the model and the loss function we defined earlier. So I think the nn value dot grad function just combines. Okay, so it uses our model and our loss function, and it basically maps them. I think in a way, it must be mapping the gradients here, right? The dependence right here itself in its memory, and then when we'll call it again and again using the loss and grad function, it will basically use them. I think that's what's okay. So optimizer dot update model comma grads. Bad type. Next dot eval. Let's read some of it. Okay, so we loaded the model. That makes sense. Get a function which gives the loss and the gradient of the loss with respect to the model's trainable parameters. Yeah, okay. That's what the basic idea of it is when we do loss dot backwards in PyTorch. So this instantiates the optimizer. And this is the basic our training loop, and then the update the optimizer state and parameters in a single state. That's what happens when we do optimizer. Right? Optim dot loss dot backwards step, right? Optimizer dot step in PyTorch. So it's the same and force a graph evaluation. I don't know what's that for. Not very sure of that. So and then basically after that we calculate the accuracy. Self function. Why is this? An indent amount does not. Why is they're all matter? This doesn't even matter. Wait, now we have this working. Now we'll be printing the every time. And in the last, I want to print total time taken. That would be here we'll do for time. Start. Should we print the accuracy right here? That should will have must have a better implementation of softmax with them, right? To me. So PyTorch people, so I'll have to use the same function. That's what it is, right? I can't use the PyTorch implementation of softmax when I'm trying to compare the performance because they might have a more optimized one than me, and in terms of maximum, I'll have to do something like that. I guess the mx dot maximum is MLX implementation, so I don't think we need to worry about that as much. Why is it MX? What is MX? Is MX? Hell, am I being it wrong? Well, is it MX in here? Why is it MX? Oh, let's do it as MX. Like it does. I don't think it will make any difference though. But again, the same names can does some error sometimes, so it's better not to use them because MLX is a library in itself, and if you use the same name as it in the alias, it can cause some errors. So yeah, so this should work. Everything is MX now. There shouldn't be any MLX anymore. Batch size is not defined. Batch size is to where did we define the learning rate? Come on, basic rule. Hyperparameters on top. What should bad code? Oh, num box is equal to num. And wow, that was so dumb. I written it like that. Learning rate is equal to A. No, learning rate is equal to learning rate for LR. Call it LR. Right. Batch size. Have you modified the batch size too? I think that was the first thing. And now the nummy box is also. No magic numbers in our code, okay? We are good guys. So everything is in place for the experiment. I think we'll be printing out the total time taken. We will take it out accuracy, and I think one more smart thing to do would be to make uh accuracy just good plot, right? Accuracy append since, and finally after time we are not including it in that. Let's import method. lt.plot accuracy range len should make sense. So no, okay. Dot plot x is equal to a comma y is, I think everything is, let me just check, does it work? It's good to have this second file your Python. If you have a second file for experiments, you could just quickly look it up. It's just like working with Jupyter notebooks, but in cleaner interface. I say this one is cleaner than Jupyter notebooks because there is no syntax completion in Jupyter notebook. The color semantics is not very great, not very helpful. This is much easier to write, basically. So I recommend using this instead of. And there is also a new notebook that has come into the market known as Merimo notebooks. So they are in the research phase right now. They are really interesting, and I've been working with them. I might make a video on them too later. So they are pretty cool, right? So Merimo notebooks, and the interesting thing about them is they give a really clean interface first of all, and basically you can import the analysis you have done with them directly as an HTML file, or you can import it as a app directly. So uh, that's pretty cool. I did work with the Merriman notebook. Uh, so yeah, we will work on that. So let's just quickly check it. So let's have our here 1, 2, 3 over 1, 4, and 9, and 16, 25, 36. I know I'm being boring. X is equal to this. Y is equal to square. Y is equal to square. For Python element 5. What happens? Got an unexpected with key argument. Okay, so plt dot. What's the problem? Okay, you don't need to give it as a keyword, I think. You can just do that. That work. I didn't see the plot. Okay, that works. But that's opposite of what I did. So I'll have to keep these here and squares here. Now it should work the way I want. To. And one more thing that I like to edit is dot x label. That would be epochs. The accuracy dot title would be accuracy. Best performance folks working. Great. So let's copy this. Leave it all here. Change accuracy. We will have done. Now our code is done. Ready for the file and run? Ready for the launch, comrades? I'm ready. So let's do Python. Nice. MS5. Are we ready to launch? One, two, three. Let's go. No errors, please. No errors. We have fixed as many errors as we. Okay, great. We get an error. Okay, wow. Just kidding. We didn't reshape this. Why didn't we reshape this? That's stupid. That will obviously give us. Let's define it right. We'll have a filter, and the filter is this guy here. All of his cool things. My god, come on. Have I done wrong? I have a two to you. And dot average cool filter to be more. Dot shape will what will reshape it to? Batch size. We'll have to use the batch size, uh, our height and width, which is 2 comma 2. You know this, we can directly use this, otherwise we'll have the channels. Will that work? Channels can't use the same filter over and over. So we can't define it as single. We have to do copy this. We have to define it. No, no. Okay. Fourth. Here instead of using this, use for we'll have to define the array in it. What we'll have to do is replicate it. How can we do? So, I'm talking about arrays. There must be a way to broadcast. Broadcast to apply broadcast to apply this. So that's so obvious. That's what I've been doing. Guys, and so let's see. Let's say we have an array, right? We have an array which is, yeah. Let's use the same array. Why not? 1 by 4 into 2 4 underscore 2. Let's convert it to. Let's also do comma, or maybe like that now, right? So int rr. array. Code array. Podcast. Oh, okay. Given the array, given the sizes. Work. If this cannot be broadcasted, this can it be? So this works. That's just yeah. It is. So what I can do is I'll do broadcast 2 comma 32 comma 2. Then I'll reshape it to 6 comma 2 comma 2. That should just work. That does work. Print out that works. Copy it. I think this work. And we are having an invalid input issue. Does it not do it in place? Let's display first. Had gotten. I think the error is X. And the only possibility is int. 56, 784. It's 1D array. You're using a 1D array. Do that. Stupid. That's what terror is all about. Fuck, that's so stupid. Here's the evil. And here also, I don't in the error would be left. Oh, expect the input channels in the gate array to match shape 4, 4. What is the input channels and the output right in the there is the con. On today. In channels, out channel. And in the batch dimension, H is the input, right? The size of right. How many positions paired? Learning bias. Great, great. What's next dot con to be? Is the error here? That's 256, 14, 14, 2 happening because of this. There is this. But me, I 250. Max one to the size is 4, 3. exercise also. That side. Your channel. I. Error is coming from the convolution, not this. Okay, so it has, but I expected it to have 30. How is that possible? The filters, how can the filter- okay, let's look at the filter. Goes in operations, right? So out. Ah, I see what channel out should. I thought this would be the bad size, but now it should. Another error. Else fine. Errors. This time it must be from the cross and cross, right? You have not. There is that. Last dimension of the first input which you have to match. Oh yeah, I have to reshape that one for doing that. X dot reshape. Guys, softmax. Did I not make these changes? And oh my god, how many? Did I not make any changes in softmax? Okay, just these ones. Out. But that was so idiotic. How did I miss? Out is equal to this for batch and X. A dot item. Happening. Let's check out the data loader. Till then, where does it import it? Anonymize timer. Might be doing. Save dir is equal to. Okay, we got value error. This size dimension of the first input, second to the dimension, second input. That size. That size. Right. So I'm so so I had these. So I also having a bad size here. Made it 6 into all of this. Now let's remove the reshape. Get the error again. Right. Where were we? Where was the reshape? So let's just remove it for now. Let's just see size we are getting is should be it should be 256 comma 6 comma 24. Right. Now I'm saying that 6 into 6 is 12. This 6 into 6 36 into 64 gives us 2304. I have written here, right? As my input dimension, the output dimension 10. Now the input dimensions also include a batch size, right? So how do we handle that batch? The question. So I think when we are talking about linear layers, you don't worry about. So it should have been just. What I don't understand is if I do it 6 into 64, this should be 2304. But when I did x is equal to x dot reshape here, that size, comma, oh sorry, -1, then it gave me basically it gave me for some case it gave me 860, which doesn't make any sense. It should be the same for any case. How can it be? We are reshaping it whenever we are passing in. Pass in. Where did we? Where did the error arise from? The rise from mx.me. The dimension was 6 in 860. So I think this is happening for a batch that doesn't have to. This is not possible. So dumb. Not possible. We print X. So it does work for some values, and then there comes it is working, right? I think I know how. Okay, now let's remove. It should not be an error, and so annoying without the progress. But I think we'll get to know the progress from the accuracy and the TQD can implement here. Okay, so one of the epochs is still live working. It is working, right? It is working, right? Cool. So now we have this training here. I think the 100 epochs are a lot. I don't think we'll be needing that much, so I'll just close the loop right now. We'll just do it for 10 epochs. I think that will be fine, and we'll keep the learning rate as and we'll just do the 10 epoch. And everything else just fine. We have checked everything now. It is giving us the accuracy and the epoch, so I think the testing is also working well. Um, yeah, great. So let's just run this now. Not from this. Now we also have to make this model on PyTorch, right? Same model. Can start doing that now. This is happening. This is happening. Start doing that. Okay, this must be annoying. I'm closing it. My phone on charging. Yay. See that? That's what we like to see. We are training in MLX by Apple. When was it released? When was it released? Tell me. And not the examples, just the whole package, man. When what is it? Come on. 4 days ago, 3 weeks ago, 18 hours ago. They're currently working on this, and we are working with this. How fast is that? That's cool. Cool. We are cool. Okay. We work on the modern things. We work on the frontier of science. I think that makes. It's fine. It's fine. Yeah. I think it was published in 2023. That's cool. Good for you. The accuracy remains the same for two epochs. That's not a good sign. I think the can we do that? Can we decrease the learning rate? Can we have a weight decay in here? MLX documentation. And let's go to Atom Optimizer. Atom. Can we have a weight decay in here? Betas. The coefficients used for computing the running averages, the term initial added to the denominator to improve. That will not help me. How can we implement weight decay? Can we implement the example? Did they have a weight decay on the SGD? This one must be more example. But right. So far, let's see. They must have a they might have used a weight decay here. I hope so. Good to use it with a weight. Eh, why is the accuracy not big question? Here's fine. That's fine. Then we do that. Now softmax it okay. The implementation of softmax I have used is it are not allowing it to backpropagate the weights. That what the problem is. I don't think so. I don't think it makes sense. What should we do, man? We implement a feed forward layer on convolution layer just want to work. Knowing now. Uh, look at the example. It's so far. Must have used convolution. With ResNet, right? They must use this convolution layer trying to define the ResNet. Um, log self.1 is equal to dimensions divided by. Hmm, that's just basic definition of a ResNet. It is changing, but on a way that be the case, that shouldn't be the case. Should start to overfit. Yep, we are doing something wrong. Wow, wow, that's ridiculous. That's annoying. Just when we thought we would, I'll still let it come. Wait, I'll look at the loop. I'll look at the graph that's been plotted. Wow, man. That was just annoying. Oh, all of string to float. Ah, okay. But it's the X. Item. I've done that. Yeah, I think. Oh well. Oh well. Ah, it was disappointing for the least. Disappointing. You guys think? Let's try to do something different. We do this is right. This is entirely copied. Dataset must have loaded right. Must have not done a mistake here, right? For the until and see it. Okay, lowest in grad function that also works. Correct. Terminal classes. Next.eval model dot parameters. Everything must have had a parameter because it NN and by default the parameters must be trainable. They didn't need to do any of that here, so I hope I don't have here. Or is it just training the NN dot linearly? That's something that is happening. The idea. Otherwise, they would have not mentioned it here, right? If it's not in the book. So let's see. Look at the conf2d layer here. Open it. Tab. It's fine. We are fine. There, there is no going to keep it trainable or non-trainable. Great, just work. So we have defined the layers correctly. Something during broadcast. So the broadcast just for the filter and but it is just like channel out. Right. What we need, I think, is that the case? Why did we? It's not. Maybe the only tab right now. So I think it would be will be better off to just not use average pooling for now. I guess not the day for it. So where is our average? And I should value it. I'll keep and then here. Um, 4 into 4, 4, 0, 4. We've gone through MX. Years, then we'll now we are using two different functions work exactly like we expected to, and we are not using the average pooling. There might be an error with the average pooling right now. So yeah, I'll be leaving it at that for now. Then the evaluation function and everything else remains the same. This also remains care of the evaluation function. Those functions pass in the reshaped value here worked channels are size here also that remains the same. Okay, let's run this one. Not using average pooling anymore. Ah man, great. Good hurt to the ego. Let's just try it though. For instance, we have mlx dot once. Uh, are we getting any error in the stream, guys? Is the stream okay? I don't think it's okay. Taken over my I think. Wow. Let's check if the because of this came up. I'm recording this hash. Okay, the stream is the only source I have. We were looking at how to make an array of ones. Array dot ones, the internet or the device. Code. It actually the code. Oh, it's OB. Power loss working better on the battery. Keep charger on. Oh wow. Oh wow. I don't even know what happened here. That's on I don't think we'll run it. Don't exception of time standard runtime error metal command buffer execution failed. Bro, that's some deep hardware level shit, man. Okay, we just have to give the shape. Apps. Code is not working with MLX. I don't know what that is. Let's reduce a dense layer, I think. It's being annoying. And let's also increase the kernel size so we can decrease this to 4x. Now it will be 28, 28, then it will become 24, 24, then it will become 20. Great. Good number. Good number, guys. Good number. Now we go 20, 20 over here. Don't give another dense layer into the mix. We don't need this stupid thing right here. We just this right x dot reshape x dot shape 0 comma minus 1, and then we pass it to the last layer. This is happening now. What is there? Last dimension of the first one, 18,432, and math dimension this. Okay, I've done some mistake in the dimension analysis. 24 8 comma 1, which and then 4, which happens. After that it should become, what is 18432? 18432 divided by 64, and then square root of this 288. 288 is the square root of what? 14, 16, and that's too big. Whoa, 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 it's not even a square. What the hell is that happening now? Also have that corrected. First layer, it should become the After the first layer, it should be 32 into 4 into 24. Whole goes to so longer than it should have. We are still here. Still 21632 match this. Why are the dimensions? Is the batch size correct? Must be. Can't be wrong. Fixed it. The error can only arise. Damn, this not the mechanical. So 2 1 divided by 8. What is the square root of? Okay, let's calm down. Let's be getting the. What is the size of MNIST dataset? 28 by 28, as I thought. Batch size is also correct. And it was working. The dimension analysis was correct when I was using our dropout mode. Or like, okay, let's print X. X dot padding on. Oh, padding on. Then why is it not? Oh my god, idiot. That's what it. Wait, now it's working now. I know it's working now. And the PC is also okay. Let it run. While that's happening in PyTorch, should be quick. We'll just follow along another tutorial. Let's just import these images. Or what? Weird error. metal. Okay. But is there some form of memory leakage that's happened? Correct. Because it will. This is all correct. Is also correct because X is itself a case of age X here and do X dot reshape minus 1 here also we'll do that X equal to X shape might be it. This might be a case of memory leakage that explains out of the. Let's just hope. It is just not working. Just working with it big. Remove a convolution. I don't know, maybe here has a lower memory for metal by MLX. Working now. I don't know. I have to clear memory. Build up is annoying. We'll have to match here. But I have not used any form of apt converting the 0 to 1. Okay, that's fair. Okay, so now it is working. So was really the size of the network then? Damn, that was absurd. I don't think you need to do this much to the test accuracy system. I don't know if it's getting updated. Training it through the whole 50,000 late. Oh, 50,000 observations for each, right? Each epoch. For each epoch, we are training it for the 50,000 training data set that we have, and the batch size for each training, and the learning rate is 0.1. So that all makes, and this training loop is perfectly matching with R. So I don't think there can be any problem in, right. You see that this should work, but it is not work. Extremely do they have a performance comparison on this, right? Let's with PyTorch, Apple. They tested it. They seem, oh, It from 0 index graph is not high. Not even getting trained for it. Specific to big. Anyone compared it in terms of like the metal device that is, look at the default device that it uses, right? I don't want it to, by default use the uh, metal device, that metal processor that they have in Apples. I want it. So let's go at, I think have to go device, default device. How do you set the device? Oh, great. The constant graph. So it's fucked. It doesn't learn anything after the first epoch. Fucked. Doesn't learn anything after the first epoch. And I think this score is, what is this? Like 0.141. What would be the accuracy if you'll guess a number between 10? The accuracy would be 10. So the hypothetical accuracy should be 10, right? 0.1. And it is 0.41. So I think it just learned something. I don't know. The slightest of the improvement from 10% of the accuracy that is naturally achievable just by selecting a random pick, it reached a 15% accuracy. It's not much of an improvement when you think. Nothing. It is learning nothing, absolutely nothing. But how can I change the device? Or why is it not learning? Those are the things that we'll have to investigate now. Fuck, fuck the idea of comparing it to PyTorch. First, we'll have to make it work in self now, because that's not working really for us till now. Device, the device. I think it's. How do you see the default device? Training time. I didn't. Enable secure coding by implementing NSLGate. So secure coding is not. Okay, we'll think about that later. Why didn't you print this? Because I haven't closed the graph yet. Okay. Oh, 55 seconds. 7.5 minutes. That doesn't matter right now because it is not. Alex. What did I do wrong? What if instead I would try that? Because that seems like a logical sense. Maybe just at all. So instead of using it like that, another linear, which will convert it from 20 will be another that will convert it of the last cookies. A1 layers, a layer. Since maybe we should just use x is equal to dot relu. We have that, so why not use it? Close it. Have a rel, right? That is the rectified. Okay, so just their implementation. Then softmax sell that layer X for the last layer and very softmax on it. Maybe even the softmax is errors. No, softmax that directly. Of this out. Because now it is it did improve a little bit. It did improve too. If now what the hell does that mean? Maybe the learning rate was too high and the epochs were too low. Um epochs. That oh it just started with great accuracy. Hell does that mean? How did it just start off with Okay, it makes sense. I guess it trained in the first. So okay, this works without the softmax training. It did get trained. So let's use the um, our convolutional layers again. On 2D, and then we'll use the input of 1, and the output channel will be 32. Kernel size. Now we'll have size of, or maybe just keep it 5. So we have a 26,20. So let's look at that. 6 and convert it to, oh, let's see if that works. Now we'll have to redo this. X shape minus um x shape 0, which is the batch size. The 250, the reshape. Oh, okay, it must have not, right? Because okay, need to reshape for that. Do that. So that you reshape it, then you should make. You're stuck. And you're stuck. So CNNs are not working. Is this the right conclusion? Or is the reshape causing so? Let's implement the reshape correctly too, right? So comes in like that, comes in like that. Yeah, I don't need to do this here. Instead, I should do it here when I'm making this. Right. Or even here. Yeah, passing it everywhere. My confusion was then what would happen with the test and test image. Test image. So let's just do it right here. Train images. Dot reshape -1. Test test. So we are changing it right here when we are getting the input, when we are processing the images, right? And then we can do is we are using convolution layer. This is happening. So this happens when we go down the first layer, second layer, which is linear layer. So we need it reshaped. So this looks like a good option. Was it's fair to do, but I think the only problem with why are we reshaping it if it's shape? Why are we wasting our times? That is, after this happens, we go to self dot layers minus x here. X is equal to x dot reshape. Uh, x dot shape self dot layers minus x, and we'll also have to apply our non-linearity. That walk. Let's see. That change. That does not change anything. Okay, it did change everything. It did change everything. Now the CNN layer training. That's great. Now we need to last thing. Now we just need to check if our softmax was working on, because that poor soul hadn't done anything the right implement. I think what we were doing wrong was we were not reshaping the data initially, and that was causing some form of an error that I don't understand completely right now. But let's just, or maybe just, yeah, let's check the softmax first. It's easier to check anyway. The softmax of these. Let's see if this is learning. La, 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 la. And it really took affected it. Those errors. I don't really understand why the reshaping causing errors. I get was you're doing in unstructured fashion. That was whatever, man. It was just an. I hope we are out of. We are not. So the softmax doesn't work. That would. Let's see one more. If it is softmax wrong, either the implementation is wrong or does not. The MLX is not able to back propagate the weights with correct, and are also correct. But softmax does work. Problem is somewhere else. Yeah. Yep. The softmax does work. Yep, it's stuck again. Okay, well, softmax. Now let's check out these. So now I have a 13. So filter mx dot broadcast to, yeah, and now we know we only have a single layer. So or maybe we just to keep it. Okay, got an error, which is fine. 256 much message in output. 546. Hmm. Weird. This error is weird. Where is it? Um, filtered layers problem. It's print text. 26 comma shape didn't decrease. Why did it not? Obviously, because we didn't apply the filter. So let's apply the filter. So x is equal to mx dot conf 2d. That's how you implement filter, right? So the operations on it's all small. So mx dot conf 2d, and here I like the input x waits to be the filter. Try to now it should get decreased right here, right here. And of a trial error technique that I'm doing right now. But I guess I've had enough with. So okay, we are getting the error on the input channels itself. So it's saying that the input is ridiculousness. Obviously, we're doing it too early. Uh, right. Softmax is fine. Now we are not using soft. Now let's see if breaks are the average pooling is working or not. I'm pretty sure that the softmax is not working. Hope it's not. It is the case with. So the conclusion is I'm not able to understand how to maintain the grade the way we do PyTorch. Like if I've done this in PyTorch, the gradients would have been maintained. Uh, and therefore the network would have kept on learning. But here, what is happening is that the whenever I'm introducing a self-made function, the network is not able to maintain its gradients. It's causing all of these errors. But main investigation was to compare the performance for now, and maybe the problem that I'm facing with this is somewhat of an therefore I'll ignore this for now. I'll implement it in the most straightforward way possible, not using a filter anymore. So it should be 20. It works, right? Okay, no. Lovely. Now why did it break? What that comes straightforward. Why is it not? It is just like that. Elizabeth, uh, be working, just working. Was that what you're telling? That change 0.1. But have I not saved it? That the yeah, I hadn't. Yeah, now it is training with this. Okay, so our target was to just compare speed. So let's see how quick. Not 100. It would take 10 each. There is no change in the accuracy, and you can even do for 5 people. No change. Hey, so and the accuracy. So it's hell is this? No, no, I just what the hell? Why is it so random? Sometimes learn, sometimes it doesn't learn. What is this? Just learned. Mind. Hallucination things now. The fuck is it? पहले. Yep, it was. I just checked that in no way that. See this. Now it is training. I didn't even change anything. It's fragile. But how can it be fragile? What is it? Is it the Adam optimizer is crossing? Let's use the one they use, right? I have no problem with it. Fine. I like Adam, but I guess we'll have to go with the other one. Check it out. Did they give any other hyperparameters other than no? So basically, I just changed the optimize, right? Adam is fragile. Adam 7.5 now. So it is learning. Yeah, it is learning. Great. Let's stick our guns to SGD. I don't want to deal with all of this. What does that mean? Wait a minute. Learning now. So maybe it will also learn with the softmax. Oh my god. So annoying. Okay, no problem. It's just stupid. I don't understand. Sometimes how I don't understand how they have fucked up the implementation of Atom. Like I have been using Atom in PyTorch from the time I've started deep learning in machine. It has never given me this kind of randomness in learning. Like sometimes it learns completely everything, it overfits to the data completely, and sometimes it doesn't know. Like, that doesn't happen when working with Atom. Now suddenly it starts to do this, and it doesn't improve after the first epoch. It just stays there. It just stagnates there. Now and instead, when I use STD, which they have shown in their examples too, it works. So maybe there is some error in the implementation of Atom they are using, right? It makes sense. Now the model is so just stuff, and that accuracy is gone. It's dead. Let's see the epoch one. So and it can't. I don't know. Maybe it's implementation error from my side. But there is no mention of it in their documentation as well. How to implement custom layers. Do they have something related to that? No. Uh, but it is not able to pass through the custom input. Not able to handle the. Okay, that was a rant, stupid rant because of this. I don't know what it is. Maybe I'm stupid. Maybe I am the wrong one. I don't know. I haven't. But it's not. It will not work with softmax. Okay, I get it. Move the softmax, so it will not work with the filter too. So cool. We don't have to make any other, and we have to make the stupid network that doesn't use a softmax layer in the end of it. Even if it's multi-class classification, it doesn't use a pooling layer with the convolution layer. But it's just fine. This is all that we have to accept because that's what is working for. And SGD just work. SGD is the gold for MLX. It Adam, I believe Adam to be the goat for PyTorch, but I think when you come to MLX, I think as SGD just takes over, it comes into its full glory. Their optimization techniques have just made SGD reach next heights. Right, great. Okay, there's that. Now let's implement this network in PyTorch, right? That's happy. Let's come back to our happy place. Um, okay, great. It learned. Let's save this. Compare this later. So figure1.png. Let's play with our desktop for now. And this is MLX SGD. Great, good job. Now let's talk about um as NN, right? Class what do we call it? N N dot mode. Now I'll have to do one thing, which is I'll have to pip install source. Okay, it's just not able to working. Torch. Yeah, it is. So great. So this Need self output dim. We'll define it exactly the same. Self dot layers and then dot uh, 2D. Let's open the let's see. And then torch dot n and course and the con channels is output channel 32 kernels. Right. Our first layer. Then I think it is the same. I don't even need anything. Just copy this. By default, find. Now we'll have forward and can also copy this some extent. Very similar. So max dot maximum. Instead of this, we'll use value layers. So back one condition. Source dot non-linear activations. Relu. Source dot nn dot relu. Here we go. Source nn nn dot relu. That then it relu dot relu there. That that makes easier. That x dot right mx dot relu also work. So the model definition is done. Loss function will use the cross entropy loss offered by PyTorch and I'll have to go for a pee break. I'll be back. So enjoy the waitings. Hello, we are back. So I was thinking about it and I thought, why not look at the implementation done by them for different layers? Maybe we'll get some hint about how can we implement our own custom code so that it works on metal device. Like that is something that we can do, right? We'll do that later on. But for now, let's just implement the same network and try to compare it. So where was I? Okay, so I was gonna implement the loss function and eval function. Eval function will basically pass in the model to this. So I think I can give you the same file. Then what are the exactly code got me argument one and four. This should work in the exactly. Yeah, let's the loss function. The loss function can be used directly. We don't need anything in there. So the loss the loss function. Source dot and loss. Forgot to look at the total time take. I hope it just um great. So here's done that. Reduction is equal to mean by default, so we don't need to worry about anything. It's the same as theirs. Then that's our loss function. And yep, loss function is done. Then loads our data. Uh, how can we load our data? Simply PyTorch. Right. So graph is almost the same, and the training time will note down somewhere. We'll our results have final. Now load the data. Load. Is equal to. I'll have to go to the experiment page again. Put in this file. I've worked with the source, source, train, train. No, no, no. Great. So we have to do this. We'll do just checked if the train data, like, what is the range of the values. For example, if I look at train data 0 image, comma 5. Okay, so comma 0. How did we use array? It was a very straightforward way to do it. That we do it. Okay, so the values are bad. Now we'll have to use transform. So transform, but we'll just do it while we're training, right? We are passing in x as a tensor. So we have to have a transform, right? We have to have a transform where will we use the, okay, okay, I get it. So this, right? Transform. Let's look at an example just to make things faster. We'll do a trans dot pose to answer. Right, that's all I want. Simple enough. Boom. Right? The hell is this? Batch size equal to batch size. Wow. Okay, let's look up. Batch size is 6 box 10. Lastly, one. Great. So that much works. Train data is equal to all of this. Transform. Right. Good. You just have to divide it by 225 later. That will. Now the only that we have left to do. Uh, First, okay, this is working. Now we have our train data. Hmm. Let's also have our test data. Similar process. Okay. Now we just pass. While they were testing this, we just passed all of it at once. So I think they did right. Eval function. Here it is. Test images, comma test levels. They passed it all at once. Great. Wow. That that their approach would be okay. Let's see how we'll play with our evaluation function. I'll have to think about that. I'm not right now. So now we can make our train loader torch dot data dot data. Mm, you'll just have size buffer is equal to. Now we can do it like that for x comma y and train loader and not the best. Then there are simple methods to PyTorch. Want to normalize this tension with the mean and standard deviation goes to on the mean to be varying between. So we'll start varying in between just like we want. Or we can just divide by 250. That will also work. Go with dividing by. Done, done, done. Better for index the network, whatever you have built, criterion, already defined it. So yeah, so this is the training process for folks. So else very good. So Yeah, he's threatening that. So I don't want that. I just want optimizer dot zero grad. Yeah. Here we have our optimizer. For that we'll have out model. Is defined now. So here are that at default in range epochs, just like we did here. So this is just like the train loader in our PyTorch. Max.eval, we don't need that. They're not necessary in this. Just have to accuracies. So we have defined the model, we have defined the optimizer, we have defined the loss, all at the same evaluation function that don't even not even need our evaluation act. So we can just do that. Yeah, okay, we'll do that. Got it. So what we can do is we can make a data loader of 10,000 batch size, and we'll pass X and Y from that data loader directly into this evaluation function. Return final accuracy, right? And this is the data loading steps. Uh, this is the model instance. For in range epochs for image labels in loader, image divide by equal to 5 output. Yeah, we should. That's how you work it up, right? Lost or backward. Finally, after this, once we have trained for an epoch, we have completed an epoch. So what we have to do is one of this. When we have completed one epoch, calculate the accuracy, append the accuracy to our item and print it. And start time and write at this start time after the loop is finished. It would end time, and while the loop after we have completed it for a hook, we did the accuracy. Let's make a test loader post util dot data dot loader test data to test data, and then you can, well, true, we'll leave it as, no need to change that. And annotate the code a little bit. So we have done that. Now, after we enter that, we'll calculate the accuracy. So we'll do eval function. What did you use to iter, right? By iter train loader, it will give me data iter. Okay. So I have to do for test load. Or I can also do it like that. Image the test function. Right. That's all it needs. Model T levels accuracy. Once we have the accuracy, we can do and print about this accuracy but item here. How does it work? And well function np dot mean dot mean. I think np dot mean don't need dot I. Right, so it will print all of that. That will mark the end of our loop. After that, this exactly the that checks out, and everything seems to work fine. Should work now. Could have also done it like that. Make it into an iterator. Call an iter for it. Instead of doing that, just do e comma t Next, just make that's good. The training. I think for the extra. Oh, they're not. Just optimizer got an empty parameter list. Okay, that makes sense. So have to instantiate layers into PyTorch. That's just the trick. I just directly copied it. So care about it. Time gives you error. But the main point is if you gain enough errors quick, I think it's headache. But you should be able to remember experience what you learned and how you can rectify it. Okay, so now training for MLX1. Let's see. Okay, can't call numpy on tensors that require grad. Use tensors.h. Where did that happen? Where did I call numpy? .np.mean. Okay, want okay, first of all, let's do model.l here. That still needs still have to tag tensor.detach. I have put that work. What happened? What? Oh, ah, that is fixed. I don't think I need kind of gradients anyway. Those doesn't need gradients. Data test loader is equal to other type, right? Yeah, I was doing. I'll just table test calculate. Right. Good work now. Yeah, another error, just as I said. What is happening? Return mean should mean. Okay. Else. So it is correct. That's correct. That's perfect. So seriousness. Mean received an invalid conversation argument. Okay, so I guess this does work. It's the experiment page. So we have one to array one. Four. It should output by the logic. P dot what? We just need R1. So So that works. That's okay. Test accuracy was 0. This is weird. Can be. So there is still something wrong with this. But argmax. Okay. That's how it's been trading. Cleaner. I wanted to use the valuation they are used about this. Can make it work, right? So add like this. Over to add argmax this till passes 000. So what does np.argmax pass? Okay, that. Huh? No, 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 no. Okay, first, one. man. Right? Getting out. That's really an. Mm. Let's look at this then. How much different can it be? 12 functions. Test loader. And labels. I think we need to do output model dot detail. Right, and tell it now. Instead, just load. Let's just have an implementation of. Y max vibrate. Don't return. It's just what does it? All once. I can return time by not training it. 10,000 10 like that. The vibrate. Correct. Okay, that's correct. Just gives false. Problem. Just give. Now it works. Now it works. Okay. So much in use. Great. Ready or absolute. Argmax also argmax this type out is equal to model x output. Those are all the mistakes and most important one that we can't forget anymore. Oh, dot number skills eager to commit a evaluation for have to do the boring stuff again. For T loader, test loader, have to do T im equal to 5. Tables. Wow. Table. Accuracy is dot append. Accuracy. And we just yeah this list of it and boom. Now it should be working. Now it's done. Damn, it's how long has it been? Half to 5 hours? Could have done some recordings. Oh my god, are you kidding me? Scared of this. Please, why are you repeating? Why are you not getting trained? What's happening now? Oh no, it's stuck. It's stuck, guys. Oh no. It is actually stuck. Not learning. Why is it not learning? Wait, you not like this? Is that what it is? Think so. Self dot L1 X. After that, you just L2X. This because of the activation layer. Gross entropy expects them in a particular range, and I'm not able to implement the softmax. Ah, so annoying. That's what that stupid. It has gross entropy in it. You're stuck again. This will run, but the problem is gross entropy loss. Part two. Yeah, it's just stuck. It's totally stuck. So great, great. Funny day today. Okay, so it does that automatically. We don't need to apply softmax before this, but we are getting stuck on the. We can change that. So parameters. Okay, we're not getting stuck. That's really interesting. Coming back to this after so long, facing these weird errors. Then I don't think the accuracy. perfectly straight line, not learning shit. We don't learn shit here. That's what the model. It was the don't. Then let's add these. Do something. Some sort of normalization. I'm missing. I did divide it by 25 points for both of them. I did take both of them are rated on. Is there a mistake in the maybe there is, right? Maybe the I don't think it's very likely though. But let's just say and code is equal to train is equal to let's just do nice. So getting an item dot as array. Let's just I bet it must be in it. I'm pretty sure it's gonna turn test it. Just because what else do we yeah it is. It is from so we have to divide it. Dividing it by a flow. There must be right or is it not? Just to make there are float or is all just zero. Great, that explains but it is all 0 point, right? Might be something. How do I check it? Images zero maybe that will help me. Only sure. Nope, there are just zeros in it. Got it, found the error. So when we are converting it to tensor, yeah, there you go. So we need to define okay, transform to tensor in PyTorch. Great, we found the error. To tensor Are you writing all it was just a lot of work. Will still keep getting should somewhat learn, should get a decent can't be that the model is there. It was able to achieve 96% there by particular here. What has changed? Okay, I don't think just guessing is that that 0.113 guessing. Not fair. Why is it guessing? Model keep getting a parameter have in have all the parameters. What did they define? Have why do I have to ponder so much into the basics for these simple tests? Done. Building the network. Let's see your code. The flow. Why is it? Why are you using sequential then? Get some. But con one. I don't even know all we use how you work. You want me to do that? I'll do that too. F F dot Z. Fine, I've done one. Then again, last one I've used percent. So while you're training it, device error, use device any in the C by default. I try Adam here. I should that help. Okay, there is some bad side, large bad. Because the bad side shouldn't cause this even when we are talking about shuffling every time. So when we are shuffling every time, the lows shouldn't be same, right? The accuracy should come out to be exactly the same, 1 1 every single time. There is somewhat else. The error lies somewhere else that I'm not able to detect right. This is weird because this is exactly how you do it. This is how I've been doing it all the time. But suddenly it doesn't this is turning into real. Well, right. Back to that's how it's they were very good. They must have. But the data set just like we did, we're just very about all of the printing stuff, training and validation, random split. Fine, you can do that. Convert validation split 2. We didn't do that. All 60,000 of 128 of batch size. All is equal to true, train, batch size, validation. Model is equal to expression. XP. That should also be fine. There is no problem with the layers. Um, Fine, it should work. Is exactly. It is. If there are just to, let's see if it works on code. Check if the bug is because happening like literally this. Let's just give everything that we need, right? Stop running. Just give it, let it happen. See if the results changes. I'm still using the CPU by the way. Could have changed. Not take that long anyway. That long of a code. It takes 60 to 76 as we saw with that one. I don't know. Wow. Ever. Same code as that one, but it's just I ask me what. Can it be that there's something wrong with the evaluation? Would it be just moving? Okay, wait. So this is a very common pattern in PyTorch, right? So it happens. So let's not call it model. Let's call it M. I've seen it happen multiple times with me. Okay. So we are calling it M. We're calling it model here, but not anywhere else. We don't play with scopes. Turns out to be bad. Trust me. So yeah, can that be it? Let's do it here. Man, this has happened to me. It's happened to me. Oh my god, I should have taken care of it. But it's just that scopes work so perfectly in Python, you never worry about these things. Um, but I think this could be it. This could be it. This is the only possibility that's left. After this, you just leave. If this doesn't. Oh man. It. This is the only thing that makes. Run it. Okay, wait. Go back to the. What we have got with ourselves. Come on. Okay. Because it's okay, this stupid. Why is this not learning? Why doesn't it want to learn? So cool to learn, no? This guy here doesn't want to learn. The fuck we do? Stuck. Just guessing. Guessing. 11% guessing. Why the fuck do you have to guess? Why are you not back propagating? Can't be. But desperate. Can't be. Too wishful. You know? Oh, why is this not working? Oh god. It just doesn't want to work at all. This stop working problem on or or whatever you have been working and suddenly working. Some stupid reason. I know there is a that is going on inside of it. That once I see it, so annoyed with myself, so annoyed with myself for wasting so many hours. But this is what it is, right? What happens? Understand something. Like if it was something that I was trying for the first time, I would have left it logging. But I was stuck with it because no, I can do it. Times that's where the belief factors. I can't leave. Can't leave a dumb model just like. Not what I have done in the, how would I suddenly right? Code is right. Then why isn't it working? Right. That's out. Now the right thing. Right, true, false, whatever it was. For 10,000, so it's what better than guessing. So where could the error be? Heck. Let's just try and know instead of divide and change let's stop dividing part of it. That change. Because when we were talking about MLX, we already had data set that had the values. The errors we were getting there were different. But here we had to go through slightly more steps when we data process because the data was between five. And there you go. We have it here. You see, that's why you don't leave things in the middle. Because if you trust yourself, you will be able to figure it out. And there you go. Now have it working just in the same way. So we have a SGD optimizer that is working, and LR model, the parameters, everything is correct. Everything is same, exactly same as the MLX one. Right. So let's see what the training accuracy comes out to be. And we'll repeat the experiments thrice. Okay. So all of these experiments that we have conducted here, we'll repeat thrice just to calculate the average. Okay. Cool. Finally have a working model, which is great. Oh my god, it was the normalization. Wow. Wow. This is something to really think about, right? Error arised just because I divided by 255 instead of normalizing in a straightforward way. Why could all the values were between 0 to 1 in my case, the way I did it. And then maybe the values were just getting. That's just. No, I know it is better to do normalization by doing that. Like the way I did it was definitely not correct. The other way to do is, which is more common, is to just, like when we normalize things, you do it like image to do minus 127.5 and this whole divided by 120.5. This is more common way of doing it, and this is considered to be mathematically more stable and better. But my use case, I was just not able to detect any difference in dividing by 255 directly. Um, I thought the values will remain between 0 and 1. That's what we want, because we want the image pixel values to be between 0 and 1, so that they don't overfit or like over expand in a sense. And we also wanted to keep it between that so that they can train easily, um, and also not have too much of weight. But I guess dividing by 225 directly was not a great idea, because I think I'm compressing the standard deviation by a lot when I'm directly dividing them, and the values must have remained. I don't know. I don't know. I don't know what happened. Like, that is what I would guess would have happened, but I can't say anything certain anymore. PyTorch, SGD. Great. We did get it working though. Now let's close this. What was the training time? 193.2876. Wow. So final accuracy, the torch is 0.979. Meaning PyTorch 193.287. That's just wow, that's just till then we can also one at a time. Oh, that's just interesting. The training time reduced by almost four folds, but the accuracy remained comparatively low. Like it reached higher accuracy faster, much faster, I'll say. But it was, but that was not the case with our MLX one. But the training time reduction is amazing. Like, oh, but we also have to keep in regard the instability we were getting when Adam also SGD of cases able to train, and sometimes we were that instability. I think this does raise a it does raise. You are reducing the training time by so much, but your training is so unstable. Sometimes the model is able to learn very instantly. Sometimes it is anything. So they are using some form of optimization that is somewhat lossy. say. It's not very generalized. It loses its stability. It's on a cost of something, right? You get improvement in your training time, but that as you have to account for it. Like you're just not getting it for free. Like an instance, for example, when you are working with Rust, for example, when you convert from Python to Rust or Python to C, you get time advantages, but you don't have to pay for them. You're just getting them because those languages are faster, because they don't have to work with the garbage collector, they don't have to work with all of those things. That makes sense. And in the same way, uh, happens in any other field when you are changing a language. For example, if you make a chess engine use Python, you will not be able to go by alpha beta pruning and MX algorithm. You will not be able to go deeper than steps, the algorithm will start getting slow. But when you are using another language, for example, C++, you will have steps of 4 to 5, much higher. And that only accounts for on the basis of that you are using a better language that will make you type more, that is more verbose, but at the same time it will give time advantage because it's asking for a lot of things for you for fund, data types and other stuffs, but that is helping it process things faster in the background. So that's good. You're getting a time advantage without any cost. That's just free. You have to just write more. You have to be a little bit more patient in your code writing, and you'll be set for it. But here, here the biggest issue I have is the instability. Like that was just too unstable, and that's not great. This again, 191.806, and the accuracy was 0.975. Yes, I think it will consistently give the same accuracy. But man, that realization, the normalization thing, man, that was so like I've done normalization so intuitively, like so commonly, like you don't have to even think twice about it. You just go there, you just apply normalization in the transformer in itself, and you're done. But I just thought, okay, we want to normalize, we want to convert it between zero. It's easy, right? It's a straightforward data set, so I'll just divide it by 255. But you see, the problem that arose was that the mean and standard deviation was not solved. The problem of mean and standard deviation was solved. The mean could have been anywhere, and the standard deviation was just compressed. But that doesn't mean the issue of standard deviation. So yeah, so yeah, that was a big lesson. Okay, that can be considered one of the biggest lesson of today. Other than writing code in MLX, I guess, right? We did all of this. We explored a lot of things inside of it. We tried to use these filters. We This is somewhat a implementation of our average pooling. It works, and this softmax implementation. But man, just the MLX, like their back propagation tree was not able to read this, no matter how hard I try. I think in one stream we can try to go through their GitHub code and we can see their own implementations of their layers so that we can understand how they are making the layers capable of being read by the tree in the back propagation step so that it can be trained properly. So that is something we can do another day. So that's interesting. Now let's conduct these tests three times and then get the results anecdoted. Um, yeah, I would say, yeah, let's see. Let's run the test again on MLX after this, and let's see if it's still unstable, which might be because how many half? I think more than half of the time we spent was on working with MLX, and I don't know how much we have missed about it. Maybe it is able to backpropagate through random custom functions, but just because of the instability it has in learning, we were not able to conduct the experiments enough number of times for it to reach that stable state where it can learn properly. So I'm not sure. We can see after the tests that we conduct right now, maybe we'll get some more idea about it. Uh, but yeah, these were results in terms of comparing these two libraries. Again, consistent. PyTorch. PyTorch is consistent. That's the best part, right? 191.903 and the accuracy is 0.980. Amazing. Right. Now let's conduct some tests. MLX should be faster. It was faster. Yep. and this time it is learning. But with Adam, it was so inconsistent. I don't know what's the problem. We can look at it. Maybe we can look at the implementation of Adam by MLX. Maybe you can find something there, some kind of an error. I don't know. There might be, or I don't know. I don't know what it was. Maybe it was the normalization issue, but I don't. We didn't even process the data there. I think the data was pre-processed for us, uh, by a lot of extent, and they had implemented their um, feed forward layer directly on it. So yeah, okay, it does learn 51.485 seconds. Accuracy comes out to be 0.946. Now let's conduct one last test, and this will be our last test of the day. Okay, so it's still learning. So yeah, and I don't know what it was. I have to investigate further to understand this. But Adam was so inconsistent on MLX, but SGD has been performing. The other issue still remains unanswered about how do we how do we backpropagate through custom functions, custom equations, custom operations in MLX, and maybe we'll figure it out using their GitHub repo and their own implementation here. That will be something we'll investigate into further. Uh, there is some gap there. Yeah, so the result seems pretty consistent. Uh, Not much to check. The time just keeps decreasing. I don't know. I think there is some form of caching going on there. Like constantly just I don't know the strategy they are using. I have not read about it much. I just found that it has maybe I'm late to find it out, but um I just find it out today that there is a ML framework that has been released by Apple and open sourced. That was the keyword for me. So I just wanted to explore that ML framework. Yeah. So we did manage to implement our MNIST on MLX, and I know you must be thinking that it was just available in the examples. And yeah, I did read through it at all, but the thing is, we tried to do a lot with it. We didn't just want to stick with the example that was given inside of it. We wanted to try convolutional layers, with pooling layers, but just custom. Not today for us. Stuck there, but it's okay. It's fine. We got our results in the end. All of these results. So these results tell us, uh, just give us a decent picture about what's going on, and I think there is, yeah, just performance in terms of accuracy. PyTorch remains on top. Uh, MLX gets stuck here. So there is some form of lossy optimization that they are doing. There's some optimization that is causing this loss of accuracy in the mode. That is something further, I guess. That's the output, the final output from today's experiments. Save everything. Wait, wait. I think I'll upload this code on GitHub if you want, and I might also write a blog on it. But that's it. Signing out for today, man. Bye bye.